All right, so today we're reviewing everything we've done so far in Unit 5 in preparation for your quiz that's today. So we're just going to go through. I encourage you to pause the video and try problems on your own, or try to get as much as you can done from a problem before going and listening to the rest of the video. Just kind of figure out what you know and then what kind of things you still need help on in preparation for this quiz today. So the first thing we started talking about when we did Unit 5 was our null and our alternative hypotheses, which led to our type 1 and our type 2 errors. So we look at this first example. We're going to practice kind of writing our null and alternative hypothesis and then identifying what those errors could come from that. So if we look at number 1, the USDA limit for salmonella contamination for chicken is 20%. A meat inspector reports that the chicken produced by a company exceeds the USDA limit. You perform a hypothesis test to determine if the claim is true. So our claim here, right, the inspector is claiming that the company exceeds the USDA limit. So that the chicken, in words, right, the chicken contains more than 20% salmonella. So for our null and alternative, remember your null hypothesis is always equals, is always equality. So this would be that your percentage equals 0.20. And then since that is not actually our claim, right, our claim is that it's greater than 0.20. That would be our alternative hypothesis. Now remember, your null is always equality. So now when we write our type 1 and our type 2 error, right, your type 1 error is that you reject the null hypothesis when the null is true. So we reject that it is 20 when it actually is. So we claim there's more than 20. So type 1 error is when we claim there is more than 20%. Right, we rejected the null, so we claim there's more than 20% when there is not, when the null was actually true. When it actually was equal to 20. And then the type 2 error is when we fail to reject the null. So we say that there is 20 when really that is not true. There was more than. So we claim there is not more than 20, or it is 20. So we kept this when we shouldn't have, when that's not true. When there is more, or all right, so again, I encourage you to pause the video, try number 2. I should just say number 2. Number 2 and number 3 on the back on your own, but we'll go over them in this video as well. So the National Cancer Institute conducted a 2-year study to determine whether the proportion of people getting cancer for areas near nuclear plants, represented by P1, is higher than the proportion of people who get cancer without nuclear facilities. So we're testing the claim that people who live near nuclear plants have a higher chance of getting cancer than people who don't. So we have 2 populations that we're looking at. So our claim in words. And this doesn't have to be verbatim, right? We're just getting the idea of what our claim is. You could write it in a different way and it'd be totally right. A higher proportion of people who live near power plants get cancer than people who don't. All right, so we're always talking about that our null hypothesis equality. So our null hypothesis would be that our people, right, our proportion of people near power plants, which is P1, would be equal to the proportion of people in P2. And since that's not our claim, right, our claim is that P1 is greater than P2, that they have a higher chance. And this would be our claim. So now when we do our type 1 and type 2 error, remember type 1, we reject the null. So we say that it's higher when it's actually, it is true. The null was true. It's equal. So we say it's higher when it's not. We accept, we're going with this one when we shouldn't have. So we claim the power plant does increase risk when it actually does not. Right? Our type 1 error is we go with our alternative, and that turns out that we shouldn't have. Our type 2 error is we go with our null hypothesis when we shouldn't have. So we claim the power plant does not increase risk. Right? We're claiming it's equal risk no matter where you live, when it actually does. So type 1, we're accepting our alternative when we shouldn't have. Type 2, we accept our null when we shouldn't have. All right, so we'll look at one more example of this. Again, I suggest pausing the video and trying this on your own, and then we'll go over it together. All right, so it says Captain Jack flies small passenger jets. These jets carry 50 passengers plus their luggage. On a full flight, these jets will perform properly as long as the mean weight of passengers' checked bags does not exceed 100 pounds per person. Ben is concerned that the passengers on a particular flight have brought unusually heavy bags. He selects a random sample of 10 passengers and weighs their checked bags. He then runs a hypothesis test and bases the results to decide if it's safe to fly. Yeah, so we're afraid that each individual person's luggage is exceeding 100 pounds. Or we could say the average right, our claim is the average weight of people's luggage is greater than 100 pounds. So our null hypothesis is that it equals 100 pounds. Right? Our mean would equal 100 pounds, but we're claiming, right, we're worried that it's greater than 100 pounds. So our type 1 error, we reject the null. So we say that it does exceed 100 pounds, but that's not true. So our type 1 is we claim the mean weight is greater than 100 when actually it's not. And then our type 2 error, we keep the null hypothesis, so we claim that it is that the mean is 100 when it is not. So we claim the mean weight is 100 when actually it is not. Okay, so hopefully that was a good run through or review of writing our null and alternative hypothesis, as well as identifying those type 1 and type 2 errors. So from there, we had two things that we had to do, or there's two hypothesis tests that we potentially have learned to run or that we run, right? Option 1 is if we're given a mean or an average, then we're going to run a t-test. We're either running a t-test if we're only given one set of information, or a two-sample t-test when we're given two different samples. And these are our conditions for our t-test. If we're given a percent or a proportion, we run a 1 proportion z-test or a 2 proportion z-test when we're given two different samples. And these are the conditions that we run when we use when we run our 1 proportion z-test or our 2 proportion z-test. So right now of our hypothesis, there are technically 4 options, right? You can run a 1 or 2 sample t-test and then a 1 or 2 sample prop z-test. So there's 4 different options of the types of hypothesis testing that we're running. And then we just want to make sure we check the conditions and run the correct test when we're supposed to. So again, I would try to go through the 4 examples and identify which of the 4 you're running and see if you can check the conditions and all that stuff on your own. But I will go over each of them in the video just as a review for us leading up into our quiz today. So this is good to have with you. I would maybe hold this aside while we're doing the rest of these examples. It might be helpful just because the conditions are there and then what types of tests we're going to be doing. So if we look at our first one here, a study is conducted in which 57 out of 104 pregnant women correctly guessed the sex of their babies. Use these sample data to test the claim that the success rate of guessing is no different than the 50% success rate expected with random chance guessing. Use a 0.5 significance level. So since we have 57 out of 104, this immediately should tell us that we have a proportion. So we're running a prop z-test. We're only given 1 proportion, so that means we're running a 1 prop z-test. So then we talk about the variables that we know. We know our N value, right? The total number of women that they talked to was 104. 57 of those correctly guessed the weight. If I want to find out my p-value, right, we would do 57 divided by 104. We don't really need to know that. It's good to know, but we don't really need to know that. But if we did that on our calculator, 57 divided by 104 would give me 0.5, roughly 0.55. And we're testing that against the claim that the success rate is no different than 50%. So we're testing it against the original p-value, which is 0.5. Right, remember, this is always the claim, what we're testing in our null and alternative, and then this information is what we get from actually running our experiment or our study. All right, so then we'll check our conditions. We have a simple random sample. Then we have, right, we did a study, so we're assuming that comes with a simple random sample. Then we have to check N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. So if I do 104 times 0.55 and 104 times 1 minus 0.55, I get roughly about 57 here. And that'll leave me about 47 here. So both of these numbers are greater than 10, so I'm good to go, right? I use my N and my p-value here to come up with these, and that tells me that my sample size is good. And then if I look here, my last condition is just to test for independence. So if I take my N value and I add a 0 to it, it is reasonable to assume that there have been more than 1,040 pregnant women. All right, so now we checked our conditions, we're ready to run our test, so now we're gonna talk about what our hypothesis is. So our claim, right, we're testing the claim that the success rate of guessing is no different than 50%. So that means that we're testing the claim that the proportion of women that are gonna get it right is the same as 50% our normal guessing when you're guessing between two options. So the success rate of such guess is no different from 50%. So this is our claim, which means the alternative to that is just the opposite. So if our claim is it equals 50, then our alternative would be that it doesn't equal 50. All right, so now it's time to run our crop Z test. So we'll go ahead with our calculator. We'll hit stat, go over to test. We're going to do a 1 prop Z test. So my original p-value is 0.5. My x is 57. My n is 104. And then my alternative is that they don't equal. So when I hit calculate, I get that z is 0.981. I'm testing against a 0.5 significance, and I got that my p-value was 0.327. So this p-value is bigger than this, which means we are going to fail to reject our null hypothesis. Right? When our p-value is greater, we fail to reject. And that means that we're going to keep our claim here, right? We're failing to reject this. So we would say there is sufficient evidence to support the claim that the success rate and I'm just restating what the claim was up here so that my conclusion is thorough. Yeah, that's a lot of the times what we're going to do. We're going to say there's sufficient evidence to support the claim, or there is not sufficient evidence to support the claim, and then we're just restating the claim so that we're being thorough and giving our full explanation when we're concluding our problem. All right, so let's go ahead and look at number 2 now. So number 2 says, suppose a drug company develops a new drug that is designed to prevent colds. The company states that the drug is more effective for women than it is for men. To test the claim, they choose a simple random sample of 100 women and 200 men. At the end of the study, 38% of women caught a cold and 51% of men caught a cold. Based on these findings, can we conclude that the drug is more effective for women than for men? Use a 0.05 significance level. So first, if we talk about our variables, right, for women, we have 100 women. Our p-value for them is 0.38, which means that, right, if I multiply n times p together, I get 38 women caught a cold. So then for men, my n value was 200. My p was 0.51. My percentage or my proportion. So if I multiply again n times p, I get 102 men caught a cold. I'm working with 2 proportions, right? I'm looking at 2 different samples of people. So this is going to be our 2 proportion Z test. So then I'm going to go ahead and run my conditions. My conditions, I have to run them for both of them. That this is a simple random sample. So we ran a test, a simple random sample for both of them. So it checks off for both men and women. Then I've got to do that my n times p is greater than or equal to 10. and my n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So here, if I multiply n times p, which we already did, we got 38. If I do n times 1 minus p, I have 62. So then n times p, again, we already multiplied together, so I get 102. That's greater than or equal to 10. And here, if I did n times 1 minus p, I would get 98, which is also greater than or equal to 10. So we're good there. So then when we check our sample size, again, this one is just testing that our sample size is not too large, that we can test that they're independent of each other. So if I add a 0 here is really the trick. It's safe to assume there are more than 1,000 women in the US or in wherever we're conducting this study. Same here, there's more than 1,000. It's reasonable to assume that there are more than 2,000 men. That's making this independent. Okay, so we're testing the claim. The company states that the drug is more effective for women than men. So if it's more effective, that would mean that your p-value is lower because you have less people getting sick. So our null hypothesis is always that these would be equal. The amount of women getting sick is equal to the amount of men getting sick. But our claim is that women, it's more effective for women than it is for men. So if it's more effective, that means our proportion of women getting sick should be lower than our proportion of men getting sick. All right, so I'll go ahead and run this hypothesis test to test that claim. So I'll go stat, test, I'll go to 2-prop z-test. So my x1 was 38, my n 100, my x2 was 102, my n value 200, and I'm claiming that p2 is going to be greater than p1. So here I get that my z value is negative 2.127 or 28 when I round. I'm testing that against a 0.05 significance level, and I get that p is 0.017. So my p value is low. So when my p-value is lower than my significance level, we reject our null hypothesis. When p is low, we reject the null. So I'm going to reject this null hypothesis, which means that I can support the claim that it is more effective for women than men. All right. Great, so we will go ahead and move on to number 3. So number 3 says a study was conducted to decide which private school was better for students academically. The study decided to analyze junior SAT scores to determine their rate of success. The following information was collected from 2 schools. School 1 claims their scores are significantly higher than School 2. So I'm given a mean and a standard deviation, which means I'm running a t-test. Since I'm looking at 2 different populations, that means we're going to run a 2-sample t-test. All right, I have 2 different groups that I'm considering. So the variables that I know are already set out for us, right? In School 1, my mean is 1,280, my standard deviation 250, my number of students 384. For my second school, my mean was 1250. My standard deviation is 200, and my number of students is 2,515. So all of that was already nicely laid out for us. So with our t-test, our conditions change just a little bit. Just that second condition changes. We still want a simple random sample. Right? We conducted a study, so we're assuming that we're doing random samples anytime we're doing a study. Then we want to check that n is greater than or equal to 30. So in this case, 384 is definitely greater than 30. And 2,515 is also greater than or equal to 30. So we're good there. And then here we're assuming that, right, it's reasonable to assume that there are more than 3,840 as well as more than 25,150 students taking the SAT. So we can claim that these are independent of the population. All right, so now when we go to look at our claim, right, School 1 claims their scores are significantly higher than School 2. So School 1 scores are significantly higher. And we could fill in our critical value because we know that value at this point is 0.05. So our null hypothesis would be that they're equal. It's always equality for our null hypothesis. But our claim is that School 1 would have a higher SAT score than School 2. So School 1 would be greater than School 2. All right, so we have all of our stuff written out at this point. So now we can go ahead and run our t-test. So we'll go stat test. We're going to go to our 2-sample t-test, number 4. And we're going to type in that data that we have. So School 1's mean was 1280. Standard deviation was 250 with a population of 384. School 2 had a 1250, standard deviation of 200, and had 2,500. And then we're claiming that U2 is less than. Always keep pooled at no. So when we calculate, so we got our t-value is 2.24 and our p-value is 0.013. So that tells us, right, our p-value is lower than our critical value. So when p is low, we reject our null hypothesis. So we reject this, which means we have enough evidence to support our claim that School 1 scores are higher than School 2. All right. So we have one more example to look at, number 4. A cleaning company claims that their product keeps germs away for more than 5 days, which is more than in any other company. A study went to 40 random houses and sprayed the product on different surfaces throughout the home. Through the study, they found the area to be germ-free. Sorry, that should say germ-free. For 4 days with a standard deviation of 1.2 days, using the significance level of 0.01, test the validity of their claim. So I know because I'm given a mean and a standard deviation that I'm running a t-test. I'm only given one population or one sample, so it's just a 1-sample t-test. So we know that our We're testing it against if it's more than 5 days. So that means our initial mean is 5 days. What we're comparing it to is 5 days. And then from our study, we got that the mean was 4 days. The standard deviation was 1.2 days. And we looked at 40 homes. We also know that our significance level we're going to use is 0.01. So we could fill that in as well. Right, remember your not value or your initial value, that either P naught or U naught is always what you're testing, what your claim is, what you're testing your study or your experiment against. So if I check my conditions that I have a simple random sample, right, we went to 40 random homes. We need our N value to be greater than or equal to 30. We have 40, so that's a good sign. And then we want to make sure that our N value is not too big. It is reasonable to say that there is more than 400 homes that could be considered for this study. So then we claim that the product keeps germs away for more than 5 days. So our null hypothesis would be that it equals 5 days, and then our alternative would be that it's more than 5 days. So this here would be our claim. All right, so it is time to run our test. So we'll hit stat, go over to test. We're running just a regular t-test. So again, that initial value that we're testing against is 5. Our mean was 4, standard deviation was 1.2, and our N value was 40. We're testing that it is greater than 5. Right? Our alternative is greater than 5. So we end up with a t-value of negative 5.27. Yeah, this should always match your alternative hypothesis. If this does not match, if this initial top statement right there does not match your alternative hypothesis, you have the sign backwards. So you need to go back to the test and change that last piece, right? When we go over here, you've got to change it to be something else because that means you got the wrong one. You picked the wrong one. So I get that my t-value is negative 5.27. My p-value is 0.09 or 0.99. It's basically 1. So since this is so much higher than that, we're going to fail to reject the null hypothesis. So we're keeping this, meaning that we're not supporting our claim here. We're keeping that it equals 5, not that it's greater than 5. So there is not enough evidence to support the claim. That the product keeps germs away for more than 5 days. All right, so that's a review of each of the 4 tests that we've seen so far, going over how to check those conditions and run our test, and then draw our conclusions. So hopefully after this, you're feeling prepared and ready to take the quiz today. Good luck.